This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, folks. Let's get started now. Thank you. Okay, so today it's back to me. It's the end of Matthias's spell on, he's been talking about information retrieval over the last few lectures, and I'll be finishing off this topic by talking about how we evaluate these systems in the first part, and then the actual secret sauce to how information retrieval engines actually work. The truth is they don't just do BM25 or TF-IDF based indexing. The formula actually ends up being a lot more complicated, and there's this mechanism by which this can be done called re-ranking. And we'll talk about that in the last half of the lecture. Okay, so re-ranking or learning to rank is sort of this last point, which I've just covered here. Okay, so up until now, from the previous few lectures, we've looked at how we make do with a specified scoring function, how we go about creating indices that can use the scoring function to find the documents that best match a query. So how we can do that in a space-efficient way, so that we can operate in memory a lot of the time and do things super fast, and also if we can do it in a way that we don't need to go very deep into the postings list, like in the case of the WAND algorithm, where we're doing this top case type query processing. Now today we're going to talk about how good the quality of these documents are. So irrespective of how fast it is or how efficient it is on disk and so forth, query engines are popular today because of the fact that they produce good results, right? And so then the question is, how do we measure quality and how do we improve quality? It's not necessarily that straightforward. It's not like we're saying we have a simple classifier and we're measuring the accuracy of how many times it got it right or wrong. It's a bit more nuanced. You enter a search query, you get often a page of hits in a specific order. Maybe you're doing it on a phone, maybe you're doing it on a laptop or another computer. What is the quality of that set of results that are given to you? And is there a way that we can distill this into a number? So it's particularly hard to characterize because we're getting this document, we're getting this big set of results in a ranked list, often with snippets and various other things. If we ask people to tell us how good it is, how good these results are for a certain query, it's going to be quite subjective. Some people are going to be looking for one thing, some people are going to be looking for another, and so forth. So were we to ask a whole lot of people given this query, we'll get a whole lot of different results. And often it depends not just on the query, but on the information need underlying. So when we search for something like Python, for instance, are we searching for information about snakes? Are we searching for information about programming languages, for instance? So that's something that would be quite obvious from an information need, but not very obvious from the query string itself. The other thing is, that's just illustrating that the information need and the query are two separate things. Sometimes the query is super specific. It's really obvious what the information need is. Other times it's much more subtle. Okay, so how would we do it? Well, the obvious way is we get humans to judge for us. So we design our algorithm until we're happy with it. We throw it in front of a person, and we ask them to say, how satisfied are you with these results? Like, you might give them a survey, say, afterwards. Get them to use the search engine for a short session, and then you ask them afterwards, were you happy with these results? Or maybe you'll say, for this page of results, were you happy with these things? Give us a tick or a cross as to whether or not each of these items were good. Maybe you check to see whether or not they managed to finish a task. So you give them some queries, some some tasks that they have to answer, like you ask them to write a short essay about a topic, they have to search for information about that topic. How has the search engine helped them to do that? Maybe you could give them a few different search engines and then see which one, or different users, different search engines, see which ones lead to better task completion. The problem is here that this requires people to do laborious, slow jobs, like this is evaluation jobs. It's very difficult to set up these experiments, and we'd like to be able to tweak our system in many different ways, and we'd like to faster turnaround than having to go out to crowd workers or students or various other people who might be working for us and doing these evaluations. We'd like to be able to get an instant result, right? Say we change the TF-IDF formula, we go from logarithmic counts to raw counts, or we play around with one of the K values in the BM25 or something, right? We'd like to get an immediate evaluation number within a few minutes, turn around to say, okay, was that a positive result or a negative result? If you have a human evaluation, then you might be waiting a week or 2 weeks, and then, okay, you can then make your change if it was a productive one, but it's not going to help you do this fast turnaround. So what we'd like to do is do this automatically. Now, the idea here is that we're trying to simplify the problem to an automatic problem, so then we can churn it through, a simple algorithm to give us a number. That number can then be used to tune the system. Now, we're not going to trust this number completely. We're going to trust human evaluations and so on more so, but this is a step that allows us to have all of these benefits of fast turnaround. And so in order to automate it, we have to make the problem a bit simpler. So the first thing we assume is that retrieval is ad hoc, and you might have seen this in your reading. I don't know if we've really talked about this so much before, but the point of something being ad hoc is the idea that you're coming in, you're doing a search, you're getting results, and then you're going off and leaving. So we know nothing about you beforehand. You're approaching the problem fresh. We don't have your history of your mobile phone usage or your location or your gender or anything else in the mix. We're just assuming this is a one-off query, performed only once, and we don't know anything about the user. Now, you might question why this is the case, because if you had this information, it would be incredibly useful. And I'm sure as you start searching things on your mobile phone, you notice that a lot of location-specific hits, say, come up, or the fact that you happen to visit certain websites actually flavors the hits that you get from Google and so forth. So Google search is not ad hoc. Google search is very situated in the context and personalized. And you can see this by putting on incognito mode, for instance, in your browser, and you can see that the research results you get for a query can be quite different to the ones when you have it on standard mode, for instance. The point of making it ad hoc means that we can reuse previous results for the same query, and we can assume that they can still be translated to this new situation. So we don't have to know the context in order to reuse the query results and the relevance results that we get from previous queries. And so the second simplifying assumption is that we're going to base our judgment purely on relevance. So when we use a search engine, we get a ranked list of documents. Each of these are either relevant or irrelevant to the query. Maybe we have graded levels of relevance, say super relevant, somewhat relevant, borderline, irrelevant, say. Maybe it's just binary, relevant versus not. But the point is that the quality of the results can be distilled down to the sequence of relevance judgments. And I'll show you some examples in a sec of what this might look like. Now, were you actually to do a search, and you're searching on Python, say, that's your string, if all of the results are about the creature, the snake, then, and you're actually interested in the programming language, you're going to think those results are terrible. You would actually generally prefer, if there's no further information, you'd like the search engine to actually give you a mixture of the two, right? To say, we're not sure, you might be asking about snakes, you might be asking about computer programming, so we're going to give you a mixture of the two results. And that's the kind of thing that these relevance judgments aren't going to be able to factor in, right? Because we're assuming that the relevance is independent, it's just the relevance each document to the information need, we're not getting an idea of what's the diversity, say, of the results. We're just looking at the rankings and the relevant versus irrelevant judgments. Okay. And then the effectiveness is just a function of these relevance judgments. So the system's going to return us K results, and the relevance of these K results are going to be the things that we use in our automatic metric. Okay, so now based on those assumptions, there are several text collections that people use for IR evaluation. So you've seen some of them mentioned before, like Gov2, ClueWeb, Trek. We've mentioned these terms before. You'll see them in the reading. We haven't really gone through these in detail. There's a collection called the Cranfield collection, which I think was referenced in the notebook. It's a nice one because it's really, really tiny. It's a good one to sort of just play with as a first step. But the idea behind these text collections, right? So they're a big collection of documents, and that's our corpus. And as well as that, we have a collection of queries, and sometimes the queries are accompanied by an information need, so they're a lot more detailed. We might have a short form of that, which is the query string, and a long form, which is the detailed information need. Then accompanying that, we have query relevance judgments, which say, for documents in the corpus, are they relevant to this information need? Okay, and typically not all the documents have QRELs. It depends on the collection. In the Cranfield collection they do, but in most other collections they don't. Simply because any realistic size collection of documents is very, very large, and the manual effort of just trying to annotate each of these for relevance is very, very tedious. So typically only a subset are going to be labeled for relevance, and that subset are actually going to be usually the ones for which BM25 thinks are good hits, for instance. So usually these test collections have come out of competitions, like Trek competitions. Every year the Text Retrieval Conference has this competition. People submit their systems. They make predictions on some queries for which we don't know relevance. And then they pull together all the answers that they produce, all of the top K documents, say top 10 documents for 20 systems. You get up to 200 documents. Some of them might be in common, for instance. And then you'll go out and get those annotated, say by crowd workers, for instance, to say, are these relevant or not? But of the other, I don't know, 1.8 million documents in the collection or something, you're not going to know. And odds are that some of those will be relevant. So this is a caveat, and this is why you shouldn't trust a lot of these metrics. And it's part of the reason why the metrics are very much based on precision and not about recall. Simply because we don't know if there are some other instances in the collection that are relevant. So we can't actually reliably measure recall. But we can measure precision. Well, we can measure precision for the systems that were submitted to Trek in the years that they were evaluated. In subsequent years, we're using that data. Okay, that's slightly questionable as well. But it's more reliable because the systems are likely to be similar to the systems submitted to the competition. Okay. Now, so let me give you an example to ground this. So this is an example from one of the earlier Treks. We've seen this before. I'll just switch onto the document camera so I can point. Hopefully that's working. Yeah. Okay, so the point here is that we have lots of these so-called topics, which is a query with its long-form information need annotated. In this case, the topic here, hopefully you can see that underline, yes. That's the kind of thing that you might query in a search engine as your keyword search. And then the description here is sort of a longer form elaboration of the information need. And the idea is that when we run our system now, we run it with our combating alien smuggling query. It produces, say, a ranked list of items here. So these are document IDs. They're in the Trek. They're just identifiers for each of the documents from the Trek indexing. You've been more used to seeing them as numbers. You can think of these strings as just unique strings for each document. And each of these has a score. So this would be the top 6 or 7 items here, right? Ranked by their, say, BM25 score. Okay, so once we have this, we're then going to, well, when these are evaluated, each of these documents is then read over by a crowd worker. They'll also read over this long-form version of the information need, and they'll judge whether or not it's relevant. So they've done this in the past, and then this is stored in what's called the QRELs, the Query Relevance Judgments file. For each document, for each query, we have a relevance judgment. In here, it's a 0 or 1, right? Saying that document AP88, so on, 140 has a relevance of 1, so it's relevant to the query, whereas this second document is not relevant to the query. Okay, so based around this run file of your IR system, these QRELs, we can merge them together to get a score. And that's what we'll be doing on the next slide. Are there any questions at all? No? Okay. Yep.
Those QRELs were, how do they choose which ones to annotate? They can kind of go exhaustively.
Yeah, they can't go exhaustively, so they choose the ones to annotate that are likely candidates. So by running a search engine, finding the top ranked 200, for instance, is one way that you could do it. And then you can just annotate those. It does mean that documents that are very relevant to the query but don't fit the kind of models that people are trying for IR are just not going to be included, which means that if you're going to use this as your mechanism for advancing the state of the art over several years, it would discourage anyone from innovating systems that are very different from the current systems, right? Because you would just judge them to be wrong when in fact often they're right. So it is a caveat that it's probably quite useful doing it this way when you're fine-tuning some parameters of your model, but if you're going with a radically different model, it may be less useful. So yeah, then the only reliable way is doing some kind of human evaluation. And maybe you then augment the collection with new QRELs, so you can then do future research.
So they do that before the competition starts?
No, they do that during, so they do this every year. So from the previous year's data, they'll do this. So then you'll have this information, and you can use that to tailor your system for the subsequent year. And then from that output, they'll then get that annotated, so then people can use it in the subsequent year, and so on. So each year there are fresh queries, so that the topics are new, but and they'll be chosen to be quite broad and cover lots of different kind of queries, maybe some that require long lists of answers and some that are very needle in haystack style kind of searches. But the idea is that they're done afresh each time. And so, yeah, when they run these competitions, they tend to run them, people submit their systems, they have a delay of a month or so, and then they get the results of this evaluation. So then they can get the final results. So yeah, that delay is needed to give time for doing these evaluations as well. But you don't have these evaluations to tune your system at that time. It's just for getting final results. Okay, so to give you an example of a relevance vector, whoops, sorry, wait a second, I've got it on here anyway. Do I? No, sorry, let me switch. Cool. Okay, so to give you an example here, oh, damn it. That's what I meant. Okay, to give you an example here, if we have these QRELs here from the document collection, we have a retrieval run. What we're going to do is we're going to look up and see that this string here, CR93H9548, it is listed as being relevant here as a 1. So our first result in our relevance vector is 1 here. Then we look to the second rank thing. Let me see, does it turn up? Yes, it shows up here and it's got a value of 0. So we put a 0 here. And we keep going down. We keep going down the retrieval run. We're just looking them up in here and reading off the value in the right column. So this is just a simple lookup operation. And then we end up with this relevance vector. And this is just listing each of the items in their order of position in the ranked list of output from the IR system and telling you whether or not they're relevant or not. Now, if you fail to find the item in the QRELs list, you would assume that it's irrelevant. So you just call that a 0. But now we've distilled, and this is the point of some of the assumptions before, now we've distilled the whole evaluation problem down to how can we have a magic way, a function that takes these vectors and gives us a number of quality. Okay. So we have to map these to a number. That's what our metric's going to do. Natural candidates that you've seen before are things like precision and recall. Now, bear in mind that these ranked lists may be quite long. We may have top 100, we may have top 1,000, we may only have top 1 or top 10. Now, if we get good results at top 1, we're probably pretty happy. versus if we have a good result at rank 9, we'll be much less happy. So we'd like a metric that could actually incorporate that in. A lot of the time we might be interested in recall. So imagine we're searching through patents and we're trying to find if someone else has come up with the same crazy idea. Say we've got a new idea for information retrieval, we want to patent it, we have to do a novelty search before we patent it, because this is the whole patent process. So we need to go through a patent database, we have to search through the collection, it's all text, we have to try and find which patents are relevant on the same topic. So we're actually interested in recall there, because if it does exist there, we have to find it. Otherwise, we're going to put in a patent and waste that money. Someone's going to contest it in the courts later. It's not going to be worth anything. Sadly, recall is very hard to evaluate because of the way we've structured these collections, because they're very large. So we tend to use precision-based metrics. And so some of the different methods, and I'll go through how we calculate these. Some of the popular methods are based on precision. So precision at K is one thing. So the precision at 1, at rank 1, is it right or is it wrong? Precision at 2, of the top 2, how many were right, how many were wrong? And so on. So we go down to rank K and then we count how many ones there were in this vector, in other words. Average precision is when we basically look at the precision at K and we look at that only for each item that was relevant. And I'll show you an example of that now. I'll click to this so I can scribble. I'm never sure which one's recording, so I'm always flipping them both over. Yeah, I probably should just try it out and see, but otherwise people at home won't be able to see what I'm doing. Okay, so we have this example. This is our relevance vector from before. I just made it up. These are not magic, these are just made up numbers. But this is basically saying rank 1 is correct, 2, 3, 4, 5 are wrong, rank 6 is relevant, rank 7 is wrong, and so forth, right? So precision at 1 is 1, precision at 2 is a half, precision at 3 is a third, because we have one item correct out of 3, and so on and so forth. I've got all the numbers down here. Now, if we're trying to work out average precision, what we do is we say, we're just going to focus on the ones here, and we're going to say, well, what's the precision at the first result, correctly returned result? And the precision here is now 1, right? What's the precision at whatever this one is? 6, is it? Precision at 6 is 2 on 6, right? So 2 out of the 6 items were correct. And then precision at 8, which is the next one, is equal to, what is it, 3 on 8, I guess? Okay, so the idea of average precision is we just take these 3 numbers and average them together. And effectively, and in fact, the way this is motivated is the idea is that you have the precision and recall curve. See that, yeah? So if I have recall across on the left, on the horizontal axis, and precision here, and effectively we're saying, well, at recall of just getting a single item, then, and I'm not going to give this a scale because I'm not really sure what the recall denominator is here, but at the first top item, our precision was 1, right? Once we get to the second item, then our precision was 2/6, so 1/3, about there, right? And at precision, once we get to the third item, our precision was 3/8. Yeah, is that less or greater? Anyway, I won't do maths on the fly. And the idea is that in the early days, a lot of these systems, they produced these pretty graphs, and then they said, okay, well, we want to distill this down to a number, so we're going to talk about the area under this graph. And we're going to ignore all these irrelevant results in the middle because they kind of get encompassed into the next prediction, the next value, right? If you get a lot of irrelevant ones, then you end up getting penalized in the subsequent values, subsequent predictions. So yeah, that's the idea of average precision. The idea is it's the area under the precision recall graph. The caveat here is that we tend not to know, this is the big question mark zone, because we don't know enough things to actually evaluate recall beyond the first few items, the ones that were turned up in the ranked list. So typically, we only use the number. We only go as far as we know the recall. So if we know that 10 items are relevant, then we'll evaluate our ranked retrieval up to when we bring the least relevant of those into the results, and that way we can then get all of these values, all of these precisions for each of these relevant ones, and we can then average them, and we get our number. Okay, and you can see how average precision is giving you the idea of how accurate you are, and if you're more accurate towards the start of the list, then this is something that's factored into the metric. So it's quite a popular metric, and by and large, it's kind of the default metric that you might use in IR. And it's called mean average precision because we take the mean of this over an entire document collection, a query collection. We might have 50 or so queries, and we're going to take the average precision for each query. Okay, and I've written many more measures exist. You may have heard of something called discounted cumulative gain, or NDCG, which is a normalized version of it. I'm not going to talk about that because it's crazy complicated, and it's not really that different from this kind of metric. Okay, another one we're talking about is reciprocal rank. This one's even simpler than average precision. The idea here is we just look to see where the first one is in our results list. So in this results list, the first item is correct, so it has a rank of 1, right? So we look at the reciprocal of the rank, 1 over 1, and we basically say this has a reciprocal rank value of 1. Now, to make this clearer, this one has a rank of 3, the top answer. So its reciprocal is a third. So it's not as good. And so this is based on a really lazy model of how people use an IR engine. The idea is that you're just looking down the top the results list. As soon as you see anything that's any good, you stop. You're very patient until you see that, and then you're not patient at all. You just stop. And the question is, how long did you have to spend doing this? How many things do you have to look through until you found this right one? So then we take the mean of this over the collection, and that gives us a number. So this is what we call the mean reciprocal rank. If these were the two queries in our test collection, then we get a mean reciprocal rank of 2/3. Now notice that this is a pretty naive metric because if we've got a lot of 1s here, there's no reward for that whatsoever, right? It's just a matter of where that top ranked one was. So this is going to be so intensely focused on the very first item and the top few ranks of item. But it is still a useful way of dealing with these kind of things, and you'll see it in practice. So this is part of the reason why I'm covering it. Okay. Any questions on these? Well, if you have, say, in both of these examples, I've done it again. In both of these examples, you only look, in the first example, you only look at rank 1, but you get no reward. So if you were completely wrong from rank 2 to 10, you don't get any reward or penalty for that. Getting absolutely everything relevant should have a higher score than just getting one item relevant, but this is not going to do. Okay, so finally, there's a whole cottage industry in these kind of metrics, and I thought I'd just talk very briefly about this one because it's the product of various folks in this department. Information retrieval evaluation is a big area and one of the focuses of Melbourne. So Alistair Moffat and Justin Zobel, who many of you may know, have been quite influential in IR in general and in IR evaluation. There's this method that they came up with that is similar in flavour to some of these methods of average precision, but it has a whole lot of, it improves it in various ways. So the idea is it's a little bit more sensitive to different kinds of users. So you have this tunable parameter where you can say whether or not this user is a patient user or an impatient user. And the way we're going to get to this is the idea of people getting utility from their search. So if people find the search results better, they're more likely to pay more money for it, say, than people who find results worse. And so they build this very simplified user model about how this utility might work. And it's designed around the idea, it's called rank bias precision. And the idea is that, if you can see this little user model here, I don't know how clear it is, they'll view the first item in the list, the rank list, and then they'll decide whether or not it's relevant. Or they'll decide whether or not they want to go on to the next item or stop. And they're going to flip a coin each time. So if they flip a coin and say that we're going to stop, they'll stop. And then if they're happy with their search results, they'll pay a certain amount to the search engine. And you can think of paying a certain amount as being a bit like clicking on an ad or whatever, or delivering revenues to the search engine, right? If they decided not to stop, then they're going to view another item in the list, and then they're going to throw the coin again. And they'll decide whether or not to stop or continue. And they keep doing this. They might end up going on for a long time, for instance, if they keep throwing heads, say, until they decide to stop. And now, depending on whether or not the coin is just a fair coin, so it's just as likely to be heads or tails, or if it's biased one way or the other, then we can model patient versus impatient users. So an impatient user is going to very quickly give up. A patient user is going to keep going and going and going. So a patient user is going to be following this little loop here, and an impatient user is more likely to either go straight through or over the top. Right? Okay, and the way we calculate this is as follows. So for this relevance vector, let me jump to this thingy. Okay, so this is an example relevance vector here. We have, so we have this ranked list. Now, you notice here that the first document is relevant, the second document is relevant, the 6th document is relevant, the 11th document is relevant, and the 17th document are relevant, right? I'm just indexing where the ones are in this list. So we're calculating this formula, wherever it went. Yeah, I can put it on the same slide. We're calculating this formula shown above. Now, if p is equal to 0.5, then I'll just get it. This, yeah, sorry, where are we? This part here is calculating these components. Yeah. So I'll just zoom out a bit. Sorry, how do I do that? Okay. So the sum is calculated by these elements here, and then we get a total, and then we multiply it by p minus 1 to deal with this component. So if you look at a column of this, it's just working out this big. This part is the sum, and then they add it up to produce the value here, and then we multiply by 1 minus p to get this last value here, right? So the first one is 0.5 to the power of 0, second one is 0.5 to the power of 1, the next one is 0.5 to the power of 5, and so that value of 5 is 6 minus 1, right? So it's, and then the next one is 0.5 to the power of 10, which is just this factor here, and so on. We add them up, and we multiply through 1 minus p, and then this becomes our figure. Effectively, you can think of it as a dollar figure of how useful these results were to the user, right? Because it's an expectation of how useful it was based around their patience level, right? And their patience of 0.5. And notice here that the numbers diminish very quickly. By the time we're at rank 17, we have a value of 0. It's so small that it doesn't fit in 4 decimal places. If they're a lot more patient, then we can see that the values don't diminish as quickly. So again, now we're taking 0.8 and we're raising it to these powers. We add up, they get a higher overall utility. They get a higher all total of this sum, but we end up with a reduced utility in total. So although they were patient, there wasn't enough stuff in the tail of the list to reward that patience. There were too many zeros. So what we see is the 0.5 one is really heavily skewed towards the stuff at the start of the list. The 0.8 and the 0.95s are much more skewed to the stuff towards the end. And you can see here the 0.95 is still getting positive utility from the stuff towards the end of the list. Okay, so that's, where are we? Okay, and then I have an example at the bottom showing you another, for another query, another relevance vector. It gets a different score because the things shown in red have changed. This one became a 0, this 0 became a 1, and so forth. And we can plug it into the formula, we can get different numbers. And you can see here that for the impatient user at 0.5, their utility has dropped. For the more patient user, their utility has gone up. For the very patient user, the utility has gone down. So it's kind of interesting that we're getting this effect, that by tailoring, by playing around with these utilities, we're actually giving rise to different rankings between these two, the quality of these two relevance vectors. Okay, and you can sort of see why, right? So we've added more relevant stuff towards the head of the list, but it wasn't right, but we paid for it by making the second one irrelevant. So the very impatient user gave up too early to get much benefit from this. The medium patience user sort of benefited from the increased stuff around ranks 3 and 5, whereas the very patient user is penalized for that there's nothing of relevance beyond rank 6 or so. So this is a much more tailored thing. You could tweak the value of this parameter based around the kind of searching behavior you expect. And for different queries and different users and so on, this is maybe quite a justified thing, instead of just saying everyone behaves like a mean reciprocal rank or an average precision or something. Okay, are there any questions? Okay. I know I didn't go through that in too much detail, but it's something that you can look at in the reading as well. Okay, so effectiveness in practice. So we don't just look at human judgments, we also look at query logs and click logs and various other things. So if you're a search engine, you have an amazing amount of data coming in. And the question is, why wouldn't you use this? This is a much more direct and useful bit of feedback that you can use. So it's indirect, it's not as fine-grained and careful a judgment as you might get if you've got people to sit down and ask them directly, is this relevant, is this not? But it is a signal that you have in vast quantities. And the question is, can we use this? Do people come back to and click on results in the result page? Do they click on the second result more so than the first result? If you have a really common query, you're going to have hundreds of thousands of results for this and hundreds of thousands of click-throughs. How can we use this? And this is a form of relevance feedback, effectively. It's indirect in that the engine user are doing this as part of their searching behavior, but it's got a lot of signal in it. So if we've discovered that everyone clicks on result 2 rather than result 1, how do we incorporate that into our metric, right? So we have a BM25 formula. It has 3 or 4 parameters we could change. But that's probably not going to be enough to re-rank or come up with a new ranking where the rank 2 item comes to the top, right? We're going to need some more knobs to twiddle to try and achieve that change. And that's the idea. And the way we do that is using machine learning to automatically learn from training data where we have, say, a whole lot of queries, we have a whole lot of click-throughs or other kind of relevance responses, either direct or indirect, and we're going to try and use that to refine our machine learning model. Now, we don't throw away all of the stuff we've done because it's a very difficult problem. BM25 gets you a lot of the way. But what we're going to do is use BM25 to get you a candidate set of documents, and then we're going to do machine learning to deal with the last step. So if we get a set of, say, 100 documents that we know are reasonable, that have good keyword match to our query, but then we're going to re-rank those 100 documents into a new order, and we're going to present, say, the top ones of those to the user. And that's the idea. So the machine learning model is given a fixed size pool, say 100 documents, and it's asked to come up with a new permutation of those, come up with a scoring for those. And it can be a very different scoring function. It doesn't have to be fast. It doesn't have to be indexable. It can be whatever you like. Right? It has to be fast enough that we can run it on the fly, but it doesn't have to be run over the entire text collection. It only has to run over those 100 documents that we've already hand-selected using BM25. Yes?
The reason to do that is exclusively because of the amount of documents that would...
Yes. But just getting something to scale. Like, yes, you can try and do something fancier that applies to the whole collection, but it does limit your opportunities for doing this. You need to, because you're always thinking about the algorithms for doing this at scale. Yes, if you have a tiny text collection, you could do something very, very fancy. But if you have a large text collection with several million documents, then you're going to have to focus on scalability in the first instance. So that's the reason for thinking it as re-ranking rather than just designing a new IR formula. Okay, so we're going to use machine learning to rank, and this is called learning to rank. The idea is that we are given queries. We're going to have some documents. we have some documents for each query. We're going to have click judgments or some kind of human judgments, and we're going to use machine learning models to try and re-rank them. And so this little figure is showing you that for query 1, query 2 through to query n, we have m sets of documents for each of these, which are labeled x. Each document is going to be described by some kind of features, and I'll talk about what those features are in a sec, but you can think about that as a fixed length vector for the sake of learning. And then attached to that, we're going to have this value y, which is the response value that we're going to be trying to learn with our model. So that might be a binary judgment, yes, is relevant, no, is not relevant. We're going to learn a machine learning model. It's going to be able to take x's, give them a y score, work out which documents are the most relevant, for instance. And then we're going to apply it to our test data. So it's going to, So sorry, the y's are sort of, let me be more clear here. So x is a collection of documents. The y's are going to be an ideal ranking of the documents. So which ones are the most relevant, which ones are least relevant, right? And then we're going to be able to apply this model to our test data. Say we're then going to score each of the documents that have been returned by BM25, and we're going to give each of those a score. Those scores are going to be distilled here. We can use them to rank the documents and present them to a user. Okay, so I'll go through that in a bit more detail. So the training data is going to be queries, documents, here D. I'm changing my notation, which is silly. It should really be an X here for consistency. And yeah, sorry, so we've jumped from K's to M's. So we have K documents now rather than M documents. And then we have this idea, we could think about actually knowing the user and knowing the relevance. In this case, we're just going to be dropping the user and just talking about whether or not it's relevant. So, and the challenges now are, how do we formulate this as a machine learning problem? How do we define features over the document and query pairs? And how do we define an objective that then is going to be useful for this ranking problem? So in terms of features, I'll just touch on a few of these. I won't go through them all in detail. We can, if we're in a search engine, we can drop this ad hoc requirement and we can just do whatever we like. So we can look at and say, which documents has the user been looking for before? So have we seen some of their previous queries, for instance? Have they clicked on certain documents before? We can incorporate that into our answer. And other things like their location, their age, and so forth. Their language, which could be a bias towards presenting documents, result documents in the same language, for instance. So these are the features we might have about the user themselves, which I think was, the part of the reason for having the U here was just in terms of the feature representation. We can actually tailor this to each user. The document features, so we can have things like IDFs and TFs and so forth in terms of which are the features that BM25 is using. So you use the length and the TF-IDF vectors. We can use them as well. But we can also use other things, like we can look at, say, the headings in the document. We can look at the format of the URL. If it's got lots of slashes, for instance, it might be a very specific thing. If it has fewer, it might be more general. We can look at things like page rank. So this is things like incoming edges and outgoing edges and so on in the web as a graph, which page rank is computed over the top of, and so on and so forth. The query features, so we can look at the number of terms in the query. We can look at if the query is a really popular query. We can look at if the query is something that people tend to only do at a certain date or a certain time of day and so forth. We can do quite a lot of things. We can look at the set of BM25 hits, which is a bit like what you do in some of the pseudo-relevance feedback kind of approaches as well. So there's a whole lot of features that you could do here. It's like a laundry list here. Search engine companies tend to develop lots of different features and they don't tell people which features work. If they told you which features worked, then they would allow search engine optimization companies to do their job more easily. And they're trying to subvert the ranking. So that's another reason why search engines are trying to be a bit coy about how they do the ranking and not make this public. Okay, so then how do we frame this as a machine learning problem? So there are two different ways. One is as a pointwise objective, and the other is a pairwise objective. There's yet another one called listwise objective, which you can look at in the reading. I won't talk about. Now, the pointwise objective, we're saying we have a query, we have a document, we know the user, and we're going to ask how relevant is this document. So we can compute the features. We're going to get a prediction from this. It might be a classification label saying yes, relevant, no, irrelevant, right? So that's the simplest way of framing it, right? It might be a regression label saying it's a relevance of 4, relevance of 3. You can treat this as ordinal regression as well, for instance. I won't go into that. We can just think about this as a binary classification problem for the sake of this class. The pairwise objective, you're given a pair of documents, and you're saying, should document 1 rank higher than document 2? And say, if it's got more clicks on document 1 versus document 2, then you treat that as a positive instance. And again, you can treat that as kind of a binary classification task there. Okay, so the pointwise algorithm in a bit more detail. We have the feature vectors for the document. We might have some user vectors. We have some features for the query. We're going to learn a model that takes this whole tuple as input and produces an output. And then we're going to be able, if it's a real valued output, say we can then rank the documents based on that value. And that can be what we send to the user. And so to fit this, we're then going to, if we know that for certain documents, yes, they are relevant to the user, then we try and learn that those Ys have high positive values. If they're irrelevant, then we learn those Ys to have low negative values. So you could train an SVM, you could train a logistic regression, you could train a lot of classifiers. And we'll look at some classifiers in the next lecture in other contexts. Okay. And the pointwise method, I won't go through it. Oh, sorry. The pointwise method, sorry, continuing. I thought we were up to pairwise. Just give me a sec. So we're training a classifier to predict this label. It has to compute the probability of relevance. That might just be binary classification. We'll sort them after the fact, and then we can return this. And we can deal with multi-classes with slightly different flavors of machine learning systems. But okay, so the pairwise thing, I'm not going to go through in detail. I've just got a little sketch here of how it works in the RankNet model. You formulate a classifier based on a pair of documents. It sort of looks a little bit like a logistic regression model, slightly fancier than that, but you can think about it this way, where you're looking at the difference in features between document 1 and document 2, and you're formulating a function over this. Okay. So in practice, this is the secret information that all the search engines are using. Yes, they will use things like BM25, but they won't use them exclusively for the whole pipeline to get you the results. Some kind of re-ranking or learning to rank is going to be used in the pipeline before presenting you the results. And the features that they use in that are often very long. I think I've talked to people at Google, and they've said there are sort of many hundreds of features. PageRank is one of them. Hubs and Authorities is one of them. But if you read the original PageRank paper by was it Bryn and what's the other guy? I've forgotten his name, but anyway, Larry Page, right? Yeah. It looks like Google is PageRank, right? But in fact, maybe it was PageRank in the first year, but after that it's changed, right? Because people start trying to exploit it. Search engine optimization are trying to reverse engineer what their formula is. If they know the formula, then they can do very well. So you have to add new features to stop these people doing this kind of behavior. If you can rank things highly, and if you can improve your ranking even only slightly, you can make an awful lot of money. And so that's exactly what these companies are doing. And it's not just limited to sort of Google and so forth. Companies like Amazon, companies like Facebook and so on, they all have search functionality. The search is quite integral to their product, and they spend many, many thousands or millions of man-hours on creating good features and creating good machine learning models for this. So the RankNet model that I sort of skipped over quickly, which was a pairwise objective, was developed by people at Microsoft and is believed to be used in the Bing search engine still, for instance, just to give you an idea of how these are used. But you need more than just the algorithm, you need all the features, and the features are very tightly guarded. So one last point is that if you do play around with these models, you need to then be able to validate whether or not they work. you can validate whether or not they work using some of the methods from the start of the lecture, but you might not want to rely on them too much. So what search engines will do now is use A/B testing. So that means that they will have, say, two different, say, re-ranking systems. They'll swap in one for another every now and then for some queries, and they'll see whether or not there's a measurable change in behavior on how people respond to one engine versus the other. Like, do they click through more? Do they spend more money on advertising, et cetera, et cetera? And then they can decide whether or not to accept the change. And that's called A/B testing. You can do it with more than two options, but that's the way it's normally framed. Okay, so let me summarize. So we talked about quite a few things, evaluating first using relevance judgments, then various evaluation metrics from precision-based ones, rank-based ones, and then this rank-biased precision, which was trying to be a little bit fancier and allow tunability for this different amount of patients. And then finally, we talked about re-ranking. The idea is we first use something like BM25, we get K documents, and then we're going to train a model to try and reorder those K documents to decide which ones we're going to expose to a user. And okay, let me finish there. If you have any questions, please come up after the lecture. I've got reading here, I should say. So the chapter reading in the textbook doesn't really cover re-ranking. I've suggested that you look at this book, which we have the online ebook for. It's an introductory chapter. We don't have to know it in too much detail. It's an entire book on the topic, but the introduction gives a nice overview. So please take a look. Thank you. I'm going to ask some more questions.
Maybe. Who knows? So this is more. You've kind of answered this. Okay. That's all done. Here we are. So I'm just trying to figure out in my head. This is skewed to the start of the list, and this is skewed to the end of the list. And what does that really mean? Does that mean that like the user is more likely to? Oh yeah.
Well, you think the patient user gets more out of the top one than this one?
No, I've just answered my own question,
Okay,
so
good.
we're all good.
Okay.
That happens sometimes. Then here, the multi-stage retrieval using machine learning. So are we starting with like 1,000 documents, labeling 100 documents using BM25, and then re-ranking?
You're starting with probably 100 million documents.
Yeah.
You're getting, I don't know, 100 or 1,000 or something using BM25, so a smallish set, and then you're running your slow machine learning over that small set.
Over that small set, not over a bigger set.
No, and then you're trying to get the machine learning model so that it finds the top 10 and scores them really highly, say, so then you can present that to the user.
So why would you rank them using BM25 before doing the machine learning then?
Because, well, depending on how you frame the machine learning, if you have to run it against 10 million documents, it's going to take forever.
But if you've got the same, if you're running it on the same documents anyway, you just get that set of 1,000 out of the 10 million. You run the machine learning model on that.
Oh, if you only have to look at the 1,000, that's fine. But at test time, you're going to get a query you've never seen before. Yeah. You're going to have to find which documents are likely to be relevant.
Yeah.
So were you to run that on the entire collection?
So, but you're only running the BM25 on 1,000 as
well? No, you're running the BM25 against the entire collection, and then you're getting a shortlist. So it's like a shortlisting procedure in interviewing someone, right?
Okay.
So which ones make the shortlist, which ones get to interview, right? I like these two stages.
But that's only for once you're for production, I mean.
Yeah.
When you train,
you can do whatever you like, but it's better if you set the training scenario to look like the testing scenario, sort of general machine learning principles, right?
But like I think you mean like actual production.
Yes,
okay.
Yes.
Perfect.
So if you'd like it to work well in that, and you're using a search engine as part of your production system to get a candidate list, it's better if you can also do that at training time. And a caveat is that you need to have enough labels for those data.
Yeah.
But if you're Google, you do,
and
because you have enough click-throughs.
On the features you mentioned, query features. So you have combinations of users, queries, and documents.
Mm-hmm.
But you don't know, like, queries are possibly infinite.
Yes. So you need to have generalizable features. So they're not just saying query equals query 25, it's query has 5 words, right? Because that's a generalizable feature. It can be used across multiple different queries. So yes, if it's one of the top 100 queries, well, if it's one of the top 100 queries, the results will be cached.
Yeah,
There's no point. You don't have to think about that. But if it's from the top, say 100 through 1,000, then maybe you have an indicator feature for that query that you're going to learn, right? That says this query likes these results, right? You can learn specific parameters for that. But beyond that, you want to have completely generalizable features, so you can apply them to the long tail of queries.
Okay.
So the features that I've talked about are sort of more the long tail features.
So are we passing the BM25 weights into the machine learning